So hello, today we'll continue the discussion on vectors. So today we'll discuss about a new topic, that is direct and indicial notation. Okay, so in the previous class we have discussed about how to we represent the vector in the primed and in an unprimed system. Okay, so let us first see. So see over here, in the previous class we have seen that how we have related the components of a vector in the unprimed system to that of the component of the vectors in the primed system. So this is in the notation. Okay, so this is the direct notation, how we represent them. So over here the Q is a matrix. So this is how you represent this thing. See this thing, V1, V2, V3, these are the components in the unprimed system. That this Q is the matrix, Q11, Q12, like this. If it is a 3 by 3 matrix, so this will be Q13, Q21, Q22, Q23, and Q31, Q32, and Q33. I am not writing the other elements, and these are the components in the primed system. So this is how we relate the components of the unprimed and the primed system by means of this Q matrix. So this Q11, Q12, Q13 are the components of this matrix, and you can compute this thing easily by the cosine of the basis vectors along the primed and the unprimed system. This is the cos of the angles between the basis vectors of the primed and the unprimed system. This is how you calculate these components, Q11, Q12, Q13, and these 9 matrix components. Okay, so now we'll find the relationship between the components of the V dash and V. So you have found it, the relation between V and V dash. How will represent V in terms of V dash. Now we'll find out that how we'll find V dash in terms of V. Okay, so let us see. So let us write this Vj dash is equal to V into Ej dash. That is the basis vector in the primed system. So this is name as equation number 5, and this Ej dash is nothing but summation of Qij to Ei. So we name this as number 6, and using the previous procedure we get Vi is equal to summation of Qij into Vj dash. Vj dash equal to V into Ej dash. Name this as 7. So in direct notation you can write that V dash, that is component of vector V in the primed system, Qt into V. V is the vector in the unprimed system, and this Qt, that means the Q transpose of this previous matrix. So this equation we name as number 8. So this is how we relate the vector in the primed system in terms of the vector in the unprimed system. V dash equal to Qt into V. Q is the transpose of the matrix Q. So let us write it. V1 dash, V2 dash, V3 dash is equal to transpose of this matrix Q, which I have shown over here. This matrix is Q, so transpose of this matrix. To V1, V2, V3. So now all the quantities which follow this transformation rule, all these equations from this equation. So this equation you can finally write this as V is equal to Q into V dash. So we name that as equation 4. So all the quantities which follow these equations 4, 5, 6, 7, 8. So this can be said to be vectors. Follow all these transformation rules. It can be said to be vectors. So this is about this vector representation. So next we go to the next topic, that is direct and indicial notation, the topic for today. Okay. So direct and indicial notation. So before discussing these things, you should know one thing, that this tensors, this tensor quantities are physical quantities. Tensors are physical quantities like mass, stresses. Okay, so these physical quantities, it does not depend upon the coordinate system. It does not depend upon this tensor quantities should not depend upon the coordinate system, because this coordinate system varies from one person to another. One person can have one coordinate system, and similarly other person can have some other coordinate system. So there must be a means to represent these quantities which is independent of the coordinate system. Okay, so it is the method. So the method of representing the tensor quantities without referring to the coordinate systems, is known as the direct notation. So this is a system by which we represent the tensors without referring to the coordinate system. So let me write this direct notation. Direct notation. So first point is, it is also called invariant notation. It is also called invariant notation. Second point, the tensors represents physical properties. Example, mass, velocity, stress, that do not depend upon the coordinate system. So such a notation is known as direct notation. And called Another point, this direct notation provides a symbolic representation for tensor operations. And does not specify how these operations are performed. So the last point, you see, this represents the symbolic, it represents the this direct notation, it provides a symbolic representation for the tensor operations and does not specify how these operations are actually performed. So for example, when a velocity vector, so when we type in the computer, we write it by V with bold V. But when we write in our copy, we write this, we do not write a bold letter, we write V and a dash below V. So this is how we represent it in our copy. Okay, now we'll discuss why there is one dash below velocity vector, this V. Similarly, for stress tensor, in computer we write a bold sigma, but when we write in our copy, we write as sigma and two dashes below it. Okay, so this is how direct notation is being used. Okay, sigma and two dashes, we'll discuss these things later, why we put two dashes over here. Now we come to INDICAL notation, the second one. So see over here. So in order to perform the tensor operations, they must be projected into a particular coordinate system. And they can be represented in terms of their components. So by INDICAL notation, so this is needed in order to perform the tensor operations, where they need to be represented in where there must be a coordinate system by which the components can be represented in terms of that particular coordinate system. In terms of their components. So here the main thing is that we need a coordinate system by which we can represent the components. Second point, this explicit representation of tensors in terms of their components is called indicial notation. This is the notation that has to be used. And tensor operations involving numerical values so tensor operations involving numerical values are performed. Example, during finite element computations. For example, a trace of a stress tensor during finite element operation. Okay. Spatial directions are denoted by indices attached generally as subscript to a symbol. So for example, mass, which is represented by m, and there is no indices because this mass is a scalar quantity. Next we come to this velocity vector, which is denoted by vi. There is one indices, that is I, which is attached to that velocity. Next there is next is this stress tensor, which is represented by this sigma ij. So here there are two indices which are generally attached as subscripts to this symbol. So there are two indices or two subscripts. Next point, the number of indices that is being attached to the symbol, which is attached to the symbol, the number of indices or subscripts is called the rank of a tensor. So this here rank is 2. In case of this velocity it is 1, and in case of mass it is 0. Okay. The last point, the range of an index is determined by the dimensionality by the dimensionality of space. For example, like this velocity vector in three-dimensional space in 3D, this I will take values of from 1 to 3. I will take values from 1 to 3. And for this stress tensor, that there are two indices, one I and j. I will take values from 1 to 3, and j will also take values from 1 to 3. So the stress tensor in 3D will have a total of 9 components. 3 into 3, 9 components, like sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, and up till sigma 3 3. So there will be a total of 9 components. So we'll in the next class we'll discuss about more things about this tensors. Okay, we'll see about range and summation convention. We'll discuss in the next lecture, and also about how a tensor is represented as a sum of symmetric and antisymmetric vectors. A vector is represented as a sum of symmetric and antisymmetric vectors. So we'll discuss it in the next class. So this is all for today. Thank you.